So, hello everyone. Welcome to my session. So this will be about how you could be fooled by your favorite cryptographic toolkit, especially OpenSSL in my case. At the bottom of the slides, you don't see it. There is a link to the presentation. I'll show you like this. It's not yet uploaded. I guess the organizers will show you how to get the final slides afterwards. So, just a few words about who I am first. Okay. So, I am an open source guy, so I mainly work with open source for now more than 25 years. I've been introduced to open source during my studies in Belgium at university end of the 90s, and currently I act as a CTO in a very small company in Luxembourg. So, for whatever that means for a company of 10 people, I just appear to be the oldest technical guy there, so I act as a CTO. I'm also one of the founders of the Luxembourg Network Operator Group there. Just a gathering of people talking about network operation in Luxembourg and trying to solve issues when you have large-scale issues in Luxembourg. I am part of the B-Size Luxembourg Revival team, so I invite you to submit your proposals, because we are looking for participants, speakers, and also sponsors. If you like, I have some stickers for you. I did a few workshops in conferences around Europe a few years ago. I've been to France presenting an OpenSSH for beginners workshop. I was also doing an NLP for beginners workshop with Pauline, also called Cookie. And I'm also part of the ACLU Luxembourg conference, cybersecurity conference review team. I have to warn you, the next slide will show you some subliminal promotion about some of my hobbies. I've been active in open source, as I said. I've been doing some work on the SSL dump, which is a tool that you can use to extract meta information about SSL flows. The idea is that I try to modernize the build system and the whole code base. I implemented IPv6, JSON output, and many stuff. I have this tool that I will present during the presentation, which is called ASN1 template, that you can use to modify binary structures. And I have this new tool which is called dispki. You can use to just pound disposable PKI, so a whole structure of CA certificates and up to a final certificate you can use on your own server just for testing purpose. Because I was tired of having to work with different long command lines. You can find all this on my GitHub, and I have my Mastodon information if you want to connect. I'm not on LinkedIn and all the stuff. Okay, so just a quick outline about the presentation. So I will just do a quick recap of what it's all about. So all the standards that we will use later on during the presentation. We'll talk how it appears that I built a tool to work on those structures. Also the story behind this present talk, the experiment I did and the findings, all the things I found, and the real-world implications, and also the analysis of data sets I recovered from a search in Luxembourg. Okay, so first let's dig down the rabbit hole of standards around ASN1, DER, and so on. So basically, we will work with X509 certificates. You probably know them. They are used for SSL connection, TLS connections all around the web. So it's quite pretty common. So what is an X509 certificate? Basically, it's just an ASN1 structure that has been encoded using probably a binary format such as DER that then can also be transported using PEM. So what are all those acronyms? So basically, a certificate, when you try to look into it with using OpenSSL, you can use a specific CLI app called OpenSSL with the mini app, internal app called X509. In this case, I'm just recovering the live certificate from google.com and pipe it to an OpenSSL command so that I can have a pretty print of the certificate. So here you can just see that this is a certificate version 3 with its own serial number, the issuer, the validity period, and the subject of the certificate. You also have many more information, but okay, let's stick to that for now. A certificate can be printed using PEM, PEM being just a transport format for text channels. So you can take a binary structure, you encode it using PEM, and you can transport it through emails, whatever, FTP, traffic, whatever. Just text. You can copy paste certificate like this. It will be easy to transport. Basically, this is just a base64 encoded binary object. So, as you may know, as we've seen on the previous slide, here we have a certificate, but PEM can be used to transport many more kind of objects, cryptographic objects. If you go and look into the OpenSSL format options man page, you will see that there are many different kind of objects you can transport using PEM. For instance, you can transport certificate, like we did, certificate request, but also keys, public keys, private keys, and many more parameters that you will use in cryptographic context. So basically PEM, I'm going backwards. PEM is a DER encoded, encapsulated content. So DER is the binary content, PEM is the text converted structure. So in this case, I'm just grabbing the certificate from Google, convert it to DER, and output it using XDump. So here you have the content in the middle, and you have an ASCII representation of the binary stuff. Okay, well, that's fine. Now, I can also simply print it using OpenSSL X509. So these are all the commands that you can use online on your Linux machine. It's probably already installed. Now, if you go back to the binary structure, it's kind of complicated to understand what's in there, unless you use the pretty print of the certificate. Actually, there is another mini tool in OpenSSL you can use to understand what's in those kind of binary structures. It's called ASN1 parse. So ASN1 parse is a mini app in OpenSSL you can use to simply read out a binary structure and explain the content of the binary structure. So let's go back to our Google certificate. So here I get it from Google, I output it to DER format, and I simply use ASN1 parse to print the representation of the binary structure as a readable text. It's not a pretty print like we did just before. It's just a description of all the objects that are present in this structure. So in this case, you see that the certificate is actually a sequence of many other stuff. A sequence here of a sequence containing some integers, some objects, some null objects, whatever, some sets, and so on. DER is just one of the many encoding format that you can use to encode ASN1 structure. DER is the one we will use because it's kind of deterministic. I mean, you cannot represent a structure in different way. Something that is possible if you use BER, which is basic encoding rules. But there are many more. You can, for instance, go to the standard, and you will see that you can simply convert the ASN1 object to some kind of XML structures or JSON structures. We're not interested into that, we just stick to DER. So, here is a grossly simplified certificate. So, basically, a certificate is a sequence, in ASN1 terms, containing a to-be signed certificate, which is basically the information that will be in the certificate itself, and the signature algorithm, so that you know how you sign the certificate, and the signature itself. The idea is that this to-be signed certificate will contain all the information about the certificate itself. The version number, serial numbers, signatures, algorithm, issuer, subject, validity time, and many, many, many extensions. I didn't mention that here. You can go to the standard to see all about this. Okay, so a few words about ASN1 itself. So as I said, it's an interface description language you can use to define messages that would be exchanged between different parties, being client-server or even server-to-server, whatever. It's used everywhere, basically, to describe protocols. For instance, you will find it in all modern stuff like 5G, LTE, and so on, but it originates from the 80s, or at least from that era. Here we are really interested in the structure that are used daily, so in the TLS SSL scheme of operation. If you're interested in ASN1, DR, and so on, I really recommend this URL there. They're doing a pretty good job explaining all that stuff, because it's quite, let's say, complex. It's not really funny to read, but okay, this text is quite okay. Okay, so now ASN1. Basically, as you've seen, there are many types of objects that you can have in an ASN1 structure. When you define an object, a protocol, or whatever, you have basically two kind of types. You have the primitives ones that are just basic stuff, self-contained, and you have the constructed ones that are more of containers for other objects, such as sequence or sets. In the basic types, you will see that you will have integers, printable strings, and so on. You can also have classes applied to ASN1 tags. Classes are just a mean to contextualize the object you will find in your own structure. So you can have 4 different kind of classes associated with all the tags, and you encode it using just 2 bits of information in the tags itself. Also, classes can be explicit, implicit. I won't enter into such details. So basically what we have is an abstract language defining a very concrete binary structure we'll find on the network or on files or whatever. Now, how do you encode, how do you go from this formal representation of a structure to a hardware-based software, concrete binary stuff? You use the encoding. The encoding is, in this case, DER, and it's a TLV-based encoding. TLV standing for types, length, value. So the idea is when you are encoding something, you just define the types you will encode, the length of the value that you will encode, and the value itself. So here you can see that you will have 2 kinds of encoding. You will have the one for the basic types that are fixed. I mean, if this is an integer, it will be probably 64 bits, so the length is known. But for a sequence, you will have to count all the objects and account for all the lengths of the object that are in the sequences itself. So that is the difference, one of the difference between DER and BER. BER being able to transport sequences for which you don't know the length yet, so that you can stream stuff with BER. Such things you can't do with DER because it is deterministic, so you have to know the length before encoding the data itself. Okay, quick summary of how it's encoded. Let's just consider the first byte of a DER object. So you will have the tag, which is just an X byte, hexadecimal byte. You will have 2 bits that will be used to encode the class, like this. This will be just bits number 6 and 7. You will have a bit that is used to tell if the type is constructed of primitive, and that's it, pretty much. You could use up to 6 bytes to encode tags, but this is not common in the certificate world because we're just using basic types that can be encoded just using 1 byte. So here is the composition of a very simple structure like this. So here we have a sequence containing 2 integers. So you have here the types and the length of the sequence, for which you have 2 integers, types, length, value 12, and again types 2, length 1 byte, and value 34. So it's quite easy to understand. Okay, so now we can parse a complete certificate using ASN1 parse, just like we did before. And you will see here that you have the type, which is sequence, the length of the sequence, and the content of all the sequence itself. Same for integer. You have the type here, you have the length, of the integer, which is just 1 byte, and you have the value. So from that point, you will see I will recover this information to recreate the structure. Okay, so now came 2 years ago, a CVA was announced. Actually, it was found by Tevis Omandi from Google. He found that using specific parameters for some elliptic curve key pair, you could make OpenSSL loop indefinitely. You will have found the information in the CVE itself. Few days later, a POC was released, and the people working on the POC just wrote that you can create that POC using an existing certificate and modifying the parameters in the structure itself. So that's what they did. This is actually a screenshot from their pages. The idea was to modify the red lines here, so the values in red, to some other value there. The problem with this kind of structure, because of the nested sequences, if you modify something, at least if you modify the length of something, a deeply nested object, you will have to modify all the lengths of the nesting object. And actually, doing this manually is a pain, because you will have to understand the binary structure and use your X editor and dig down, and it's trial and error, and it takes a large amount of time. So I saw them struggling with that. And it reminds me that 2010, I wrote something that could help them working with that. So actually, in the ASN1 parse mini application you will find in OpenSSL, there is a special option called genconf, which is basically just an entry point for another function that is ASN1 generate endconf. So what it does, I will explain it later. I presented my tool at PTS, so Pass the Salt in Lille 2023, and as a lightning talk also at Akalu 2023. This is important for the next slide. So basically, how it works. Simply grab the output of ASN1 parse, the one we saw just before, and just create an internal structure that I simply cross recursively, just in order to output something in the format that is expected by the genconf option of ASN1 parse. So I wrote this tool in 2010, and back then there was no tool such as DARE-SKI. Also, this tool is interesting because there is no heavy dependencies in it. You don't need to install Rust, Go, or whatever. You just download the Perl script. You have the OpenSSL toolkit already on your system, and that's it. So basically how it works. So you have the ASN1 parse representation of the structure. Here is somehow complex nested sequence stuff. Here I simply launch the tool on a test DER structure, and you have what I call the template. The template is just a file that you can use later on to recreate the structure. So here I use genconf with my template, and I create a reconstructed structure based on the description I just got from the tool. So here I printed the certificate, and if you diff the original file and the new one, you see that they are the same. So basically I can go to text and back to binary, and I can do modification in between. So that's what we're doing here. Here I replace an integer of value 1, 2, 3, 4, 5, 6, 7 to a printable string hello. So I'm just working on the text file, the template text file, simply replacing this. And if you compare it to the original structure, you see that the binary there is different. Also, the length of the sequence, the top level sequence is different. But with this tool, I don't have to do it manually. I can use it right away, and it's just a matter of a few seconds. So, now the story behind this talk. As I said, I did a lightning talk about this talk in Akalu in 2023. And last year in October, Alex, the organizer of Akalu in Luxembourg, asked me if I wanted to do a lightning talk, a new lightning talk. I said to myself, okay, maybe I can. Maybe I can talk about the modification I made to the tool. But actually there was not many. But I remember something. Back then when I developed the tool, I wrote something interesting. I wrote in the README file of the GitHub that ASN1 parse, ASN1 template, so my tool doesn't work if there are some line breaks in the output of ASN1 parse. And I said, okay, maybe I can exploit that to find something. So here is an example. Actually, I used a corpus of 1.7 million certificate back then to develop the tool and tweak all the heuristics in order to work with UTF-8, UTF-16, and all the many formats of string you can find into the wild. But I struggled with simple stuff like you have here in this simple example where you have a line break into the text, because ASN1 template just used the output of ASN1 parsed line by line. Also, I looked into GitHub, the OpenSSL GitHub, and I found someone complaining that sometimes in the smime section of certificates, you could have some control characters that are interpreted. Okay. But it was not exploited. There's just an example there, and that's it. So now let's go to the experiments I did. So I was seated in the room like to do right now, and I was trying to find a way to exploit the fact that some characters seems to be interpreted by the OpenSSL X509 tool. So my objective was to print an NCArt file using the tool unchanged tool. Why that? Just because this kind of NCArt uses color changes, control characters, terminal escape sequences, and so on. So if I can manage to do that, I will probably be able to do many more things. I used two approaches for that. First one was using a CSR configuration file, which is a certificate signing request you can use. I will show you an example later on. But also I used ASN1 template with large amount of reserved space so that I could inject some binary content in there. Binary content in this case being just the NCArt. So a few words about terminal control character and sequences. So you have, as far as I understand, three useful classes of them. First one are the simple control characters that will simply just go to the next line, go back one character, go up, go down, whatever. You have control characters, control sequences that will control the terminal, and you will have control sequences that will control some part of the OS. So most of them are, let's say, disabled these days because it was exploited to launch tools just before, because you just printed some text on your screen. You could have looked at this excellent talk by Stock. I was referenced by the program committee here at Nullcon to this talk because I wasn't aware about it. He does a pretty much very good exercise of showing all kind of exploitation techniques you could use with those kind of characters. So now, if you look at simple control characters, you will have the 21st byte of the ASCII table that can be used. Here are the more interesting ones that are mainly used for movement of cursor. We'll use that later on. Interestingly, you will have the last column here that prints the output of the control character that you will see if you use tools such as less to pipe your content. Here is an example of a terminal escape sequence. In this case, I just use it to change the color of text and just reset it to the original value. So here you can see that I'm using a CSI, which is a simple sequence to switch the color and then go back to the original one. Nothing complex in that. So first finding. While playing with all this, I found that in 2021, someone introduced a way to interpret UTF-8 in certificate distinguished name, which is the place where you will find the C name, so the command name, the organization name, the organization unit, and so on. So basically all text. So if you look at the version of OpenSSL, it's active since version 3.2.4. And interestingly, as a side effect, you would have also interpretation of control characters. So here I reference the pull request that activated it. I reported that to OpenSSL, and 2 days ago, originally they thought, okay, this might have security implications, and 2 days ago they said, okay, no, for us it's just a bug, so we will just fix it. So right now this is fixed. But if you use your own OpenSSL version, probably on your machine, it's not yet released for your distribution. So here is a very small example. So I have on my machine many different ways to switch from one version to another of OpenSSL. So here is 3.0.16, which is in the line of the one you will find on a simple classical Debian stuff. So if I print a certificate, oops, sorry for that, you will see that, okay, it's properly escaped. So in version 3.0.16 of OpenSSL, it's fine. Now, if I switch to the most recent one, which is 3.4.1, you will see that I can print NCR in the certificate itself. So, okay, so the concept is okay, it works. To reach this point, I had to mangle the file itself, because you can't use all the characters. You have to tune it a bit. You will find all in the repository when I manage to upload it. And there is an interesting fact with this file. If you look at it, you will see that the data is printed from the CN section, but afterward there's nothing. So there's something that blocks the output, and that's pretty neat. You will see why. So this is the RCR with the older version of OpenSSL, the new one. Okay, and here you see that if you're using text injection, basic text, it doesn't stop the output. So you have two different signatures in this case. So why is that? So here is something interesting I found out. Actually, I will show you. It will be easier to understand. So I have a first file, which is called blah, which just contains 2 lines of text. I have a second one, which is called blee. Okay, same contents. And I have a special file that I can put in between. Now, if I simply cat all those 3 files, the output is just the output of the first one. You don't see the last one. Interestingly, if I grep for blee, it's there. So I was like, oh, what is that? I investigated, and actually this works with GNOME terminal. This works for the other terminals, but not all terminals. So it will depend. Okay, but it's very interesting for what we want to do later on, because we can block the output of the old text when printing something. So if I apply this to text, I can inject another certificate in a given certificate and simply have the output to be stopped. Third finding, and this one is really interesting because it works with all versions of OpenSSL. If you inject something into the DNS field of the SAN record of a certificate, it will be simply output printed with a row with all the escape characters being evaluated. So let's do some demo on this one. So here is a file that I use for creating a certificate. This is an actual configuration file, being a certificate request configuration file. What you see is the usual data, and you have this subject alternative name section that defines a first DNS name in which I inject some content. So all you see here is the text and some end of line that will be evaluated by the terminal. So now, if I simply try to print the certificate itself, you see that the certificate I get is a certificate for Google. That's cool. But actually, it's not a certificate for Google. This is just content I appear to be appended to the end of the certificate. If I pipe the output to less, I will see that actually the certificate is for blah.lu, but in the SAN section of the certificate, you have many more information that will be evaluated. And in this case, I used first here the character at the very beginning of the sequence. I use a clear screen so that when you print the certificate, you will see that there is a large amount of blank text, and you have the header of the original one there. So actually, I can print, when you want to print a certificate, I can print something else. So, okay, that's cool, but can we do something useful with that? Yeah, we can. Actually, Okay, yeah, we'll have different results with different versions of OpenSSL. It works with some other cryptographic toolkits such as GNU-TLS, the NSS, Netscape, Firefox stuff, the Java key tool, and so on. So you have to test it if you want to evaluate all those different toolkits. But how can we exploit this? Actually, we can exploit this by creating certificate requests that contain something else. Let me show you. So here is certificate request that will, when I print it, it looks like this one is completely self-contained. It looks like this is for subject blah.lu for the domain name. That's fine. You have subject alternative names here too. Okay. So as you can see, it's quite clean. There is no special stuff. There is nothing suspicious in there. Now, if you pipe the exact same output to less, you will see that actually the C field, so the country field of the subject, is injected with something else. And actually, the certificate itself is for cn.start.google.com. And that becomes interesting. Because if you can submit this certificate request to someone for it to be signed, you will not sign a certificate request for blah.lu, but it will sign a certificate request for start.google.com. So that's the whole point of the presentation here. The thing is that if you try to exploit that with commercial CA, such as Let's Encrypt or whatever, this one is not commercial, but public CA, it will be refused because such a complex value in certificate cannot comply with the certificate policies. So it will be refused. But if you are working in a private environment for your company, and especially if you're using some things like easy RSA for OpenVPN, you will work with certificate request. And if you print a certificate request like this with easy RSA, it will simply use the same command as this one, and it will output the certificate like this. And if you're not suspicious enough, you will actually sign a certificate for start.google.com in your own company with your own CA, which is probably trusted by all your computers. So an attacker could impersonate google.com in this case. So let's move on. So was this technique ever used? So I contacted the local CERT in Luxembourg, which is called Circle, which is a CERT for the private sector. And they provided me, I think it was 100 million certificates, but actually I managed only to download half of it before the presentation here. So just a quick rundown of the size distribution of the certificate, because this is already interesting. The smallest one is 239 bytes, and the largest one is more than 35 kilobytes of information. So it's really interesting. So we can dig into those certificates just a bit. If you look at the large one, so this is the largest one of the data sets. It's actually a completely internal certificate. It's not a valid CA that signed this one. And you will have subject alternative name that is really, really, really long. And I have many examples of such things. If you look at the small one, it's very small keys, really valid for a long time. There is no subject, no issuer. Okay, whatever it is, I don't know. So now let's look at some oddities I found out in this dataset. Here you see 3 examples of variable expansion failures. So the certificates were generated, but with the text of the evaluation for the variables itself, not the variables, not the content, but simply the name of the variables. You sometimes find this in the spam emails you receive. Another one here is some JavaScript, some JSON content, and some certificate. So it's not uncommon to see those things. Probably it's used by some applications. Oh, this one is interesting. Somewhere I found many, many examples of this. These certificates here, actually you can see that there are some backspace characters in there. So actually, what is this? It's just like track changes. So there is a cryptographic toolkit, or maybe a front end, I don't know, that output the track change in the input field of the certificate forms, probably. Here you can see that the person wanted to type Hotmail, so he started with OTM, went back 3 characters, and simply correct the Hotmail name. I have many examples of this. Another one, this one is simply cryptographic content in the certificate itself. Again, in some extension of the certificate. I have a few examples of this. I have no information about what it is, but okay, you can find that. And I also found some more complex example of control character injected in some fields. They don't do much because actually this just resetting the screen, but it's not really exploit like I showed you. For instance, this one is just going back to the beginning of line. Was it intentional? I don't know. Okay, so as a conclusion, I would say that for user perspective, but okay, it's not new. Printing control characters should be a conscious decision made by the user itself. And as a recommendation, I would say that you should use, sometimes pipe your critical content to something like less, so that you will see the actual control sequences from the output itself. I have a last demo for you. Before the questions, this demo is pretty simple. Actually, I was looking into funny things. So here I have a very large certificate file that is, if you look at this, 23 megabytes. It's completely valid. The thing is that I wanted to print NC-art, and I said to myself, hey, can we use a certificate to print an OpenSSL X509 to print to output a video? I said, okay, there are no control characters to pose between the output, so it was not easy. So what I did, I built a file containing just 16 frames, and in between, I'm just losing time printing stuff that I simply erasing, and then give this. So if you print this certificate, which is completely valid, you will have a basic certificate and a lot of content. Being control characters, being just writing stuff, removing stuff do the posing. So I think this is like 1 or 2 megabytes of data just for posing between frames, and just a few bytes for each frame. So if you do it again, you will see it. Okay, that's it. So thank you for
your attention. Do we have any questions? We can take one question.
See you next time.
Anyone? Any questions? No?
Thank you.
All right. William will be around, so you can connect with him in offline and take it further. Thank you. Thank you so much, William. Ladies and gentlemen, please give him a huge round of applause.